We now move to a particularly important topic, and that is the oxidation and reduction reactions of organic compounds. We're just going to take a very brief look at an extremely important topic, a topic that could easily take up 2 to 3 volumes in and of itself, if not more. So let's define oxidation and reduction in the context of organic chemistry. So when we talk about organic compounds, we say that a molecule is oxidized when the number of carbon-oxygen bonds increases and or the number of carbon-hydrogen bonds decreases. Technically, it can be any bond between carbon and an atom which is more electronegative than carbon. But I find this to be a simple enough definition, and that's why I'm going to stay with it. So the number of carbon-oxygen bonds increases and or the number of carbon-hydrogen bonds decreases. The opposite is called a reduction. So we say an organic molecule is reduced if the opposite happens, namely a carbon-oxygen bonds goes down and or carbon-hydrogen bonds increases. So an example was chapter 11. We saw hydrogenation reactions. Remember, we added hydrogens to an alkene. What kind of a reaction would those be? Well, you're increasing the number of carbon-hydrogen bonds, so that is a reduction. We say that alkenes are reduced and make alkanes. Now we're first going to focus on oxidation and reduction of alcohols, and we will also look at how this relates to 3 other functional groups, aldehydes, ketones, and carboxylic acids. So remember, we said a primary alcohol is a compound which has an hydroxyl group bonded to a carbon, and that carbon is only bonded to one other carbon. So 1-propanol is a very good example here of a primary alcohol. So important rule to know. When a primary alcohol is oxidized, an aldehyde is formed. So when we oxidize a primary alcohol, it becomes an aldehyde. Now incidentally, this reaction rarely stops there. It usually continues on. But for right now, let's just take a look at this and see if it makes sense. So this carbon had 2 hydrogens. It was bonded 1 time to oxygen. What happened in the changes here? The carbon is now bonded 2 times to oxygen, so we increased the number of carbon-oxygen bonds. And this carbon was bonded to 2 hydrogens. It is now only bonded to 1, so we lost a bond to hydrogen. So that is, by definition, an oxidation. So make sure you make note of this. Primary alcohols are oxidized into aldehydes. Now, as I mentioned a moment ago, aldehydes are often just an intermediate going to a more complete oxidation. So aldehydes, when they are oxidized, become, what is that functional group right there? That is a carboxylic acid. Let's again see if this makes sense. Aldehydes have, that carbon has 2 bonds to oxygen, 1 bond to hydrogen. Look at the product. The carbon now has 2 bonds to oxygen there and another bond to oxygen there. So a total of 3 bonds to oxygen now, and that carbon is no longer bonded to any hydrogens. So it is an oxidation by definition. If this is at all confusing, go back and look at the definitions of what is an oxidation and what is a reduction that I just gave you a few slides back. Now, we haven't just learned oxidation reactions right now, we've also learned reductions. Because any of these reactions done in reverse would be a reduction. So carboxylic acids becoming aldehydes is a reduction, and aldehydes reduce to form primary alcohols. Secondary alcohols. Recall those contain a hydroxyl group bonded to a carbon, and that carbon is bonded to two other carbons. They can be oxidized to ketones. So a ketone can then be reduced backwards to form a secondary alcohol. Tertiary alcohols are not able to be oxidized. And the reason for this is there are no hydrogens bonded to the carbon of a tertiary alcohol. You must have hydrogens on that carbon for it to be oxidized. Now, we will technically see phenols are able to be oxidized in a future lab experiment. That doesn't seem like it should be the case because phenols look like tertiary alcohols. The carbon that the OH is bonded to has no hydrogens on it, but they will be an exception. Not an exception you need to memorize, but I just don't want you to be too shocked when we see this exception in the lab. Now, we can give specific chemical reagents that will tell us what will oxidize something and what will reduce something. We call anything that causes an oxidation an oxidizing agent, and anything that causes a reduction a reducing agent. But let's look at a simplified method first. So for an oxidation reaction, it's usually just easier to write the letter O in square brackets above the reaction arrow. And so here we have a what? What kind of a compound is this? It's an alcohol. What kind of an alcohol? Well, this carbon is bonded to 2 carbons. So it's a secondary alcohol. What other bond is there? We only see 3 bonds, so that means there must be 1 hydrogen right there that we don't see. What did we say happens when we oxidize a secondary alcohol? We get a ketone. So this stands for a chemical called an oxidizing agent, and there's many chemicals that will do that. If we want to do a reduction, we can just put an H above the arrow. And so if we go ahead and take a look here, we have an aldehyde. What happens to aldehydes when they're reduced? Aldehydes are reduced to form primary alcohols. So you'll notice you have 3 carbons here. You must still have 3 carbons here. So you can't just say any alcohol. It has to be the one with the same number of carbons. So the alcohol with 3 carbons, that's a primary alcohol. And that's what we would get right there. Incidentally, and because the book does give us a specific example here, hydrogen is very often listed as the chemical that would do this. So sometimes you'll just see H2 over platinum, just like you did with alkenes, and that will usually work. So let's take a look at a summary of the reactions that we just looked at. So again, primary alcohols can be oxidized to aldehydes. This is again that arrow with a letter O above it. Aldehydes oxidized to carboxylic acids. And then the reverse are reductions. Secondary alcohols will oxidize to ketones. Ketones reduce back to the same secondary alcohols. Tertiary alcohols are not listed because, again, a tertiary alcohol cannot be oxidized. And there's no reverse reaction because there's nothing that you can reduce to give you a tertiary alcohol. So that's why they are left off of here. A point I really want to emphasize that I don't think I specifically wrote down here, but I did discuss. Please note that the number of carbon atoms does not change in this reaction. So that should make it easier to predict products. Your textbook does give you a specific reagent for this oxidation, and that is this compound right here. It is called potassium dichromate. It is very commonly used for oxidation in very acidic environments. And so since it is an oxidizer, what happens if we add it to primary alcohols? Primary alcohols, remember, are oxidized to aldehydes. However, it turns out aldehydes are even more reactive than alcohols, so the reaction continues, just as we showed on the previous slide, and it goes all the way to carboxylic acids. What about secondary alcohols? Secondary alcohols are oxidized into ketones. Tertiary alcohols, you're not going to see them because they don't oxidize. Now, this is going to be an important part of a lab reaction, and that's why we list it here. Potassium dichromate is red-orange. When it reacts, it changes into the green chromium-3 ion. So this tells you that a reaction has occurred. Think about this. How is this a useful reaction if we're trying to tell compounds apart? Well, if we add this to a primary alcohol, this will turn green because it will help oxidize the alcohol. If we add it to a secondary alcohol, again, the solution will turn green. If you add it to a tertiary alcohol, there's nothing to oxidize, so we would expect no reaction, and we would expect that this would keep its color of red-orange. And so that is why it's a useful reaction for us in this class. It also is used occasionally in breathalyzers because we can analyze the breath for certain metabolic products that are given off when alcohol is broken down in the blood, and we can look at the amount of change from red-orange to green to characterize a blood alcohol level. Another reagent, which is actually quite fascinating, is Tollin's reagent, and we use it to perform what is called a Tollin's test. With Tollin's reagent, we add a mix of silver oxide and ammonium hydroxide, and it only works with aldehydes. It changes aldehydes to carboxylic acids. The silver becomes silver metal, and it transforms any glass that it's on into a mirror. And so it is called the silver mirror test for that particular reason. So it's a fascinating reaction. It's also one that I don't really like to do with students for two reasons. Number one, it effectively destroys the glassware because it's now got a silver mirror on it. Actually, three reasons. Number two, this is expensive. And number three, the side products of the reaction from the silver oxide and the ammonium hydroxide are the compound silver nitride, which unfortunately is explosive. It is possible to render that compound safe by quickly adding acid to it, but if for some reason we should forget to do that and the solution should dry out, we now have an explosive on our hands, and that creates, of course, an added danger in the lab which we would rather avoid. We will use these compounds in lab, and we will see them in homework problems, but I do not want you to memorize the formula of potassium dichromate, nor do I want you to memorize Tollin's reagent. I want you to, if you see it on homework, know what you're doing. You'll have your book open when you're doing that, so that's totally fine with me. But for all the questions I'm going to ask you, which are based on oxidation and reduction, it is going to be totally fine to use the method that I showed a moment ago with the letter O for oxidation and the letter H for reduction. We are going to close this video lecture with another pair of oxidation and reduction reactions, and that is relating to thiols. So two thiol molecules can join together and form a disulfide. This is an oxidation because both of these molecules are losing bonds to hydrogen. The opposite process would be a reduction, and that would just separate the thiols and add hydrogen to both of them. So again, it's a reduction because in this case you are adding hydrogen. Now, in and of itself, this doesn't seem like a particularly important reaction. However, it's going to be critically important when we discuss the structure of proteins. Disulfides are very common in proteins and allow a protein, in some respects, to hold its shape. So we will see this reaction again coming up in chapter 16.